I have a dream that one day
T minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition and liftoff of Ares 1X, testing concepts for the future of new rocket design.
The limit of f of x as x approaches a equals L, if we can make f of x arbitrarily close to L, in other words as close to L as we wish, by taking x sufficiently close to a from either side of a, but not equal to a. Note that this is called a working definition of the limit, since it's not rigorous enough for it to be the formal definition of the limit. The formal definition of the limit is known as the epsilon delta definition. Also note that we use arrows to write f of x approaches L as x approaches a. In the next 7 examples, we're going to try and get an understanding of what this definition says. Then in the 8th and last example, we're going to revisit the definition and have a more technical approach to the meaning of it. Please note that in many of these examples, I've exaggerated distances on the x-axis for the sake of illustration. Let's start by having a look at the function f of x equals x plus 1. The graph of this function passes through -1 on the x-axis and +1 on the y-axis. Let's say we are interested in what happens to the function values as we approach 1 on the x-axis from the right or from above. We can start by plugging in a value fairly close to 1, such as 1.1. We find the corresponding function value by substituting 1.1 into the equation, and we find that the corresponding function value is 2.1. We can take a number even closer to 1, but still above 1 on the x-axis, such as 1.01. We substitute it into the equation, and we find that the corresponding function value is 2.01. Let's take a number even closer to 1, but still above 1 on the x-axis, such as 1.001. We substitute it into the equation, and the function value comes to 2.001. So we can continue plugging in values closer and closer to 1, but above 1, and then find the corresponding function values. And what we see is that as x approaches 1 from above or from the right, f of x approaches 2. We now want to see what happens to the function values as we approach 1 on the x-axis from below. Once again, we can substitute in values closer and closer to 1, but below 1, and find the corresponding function values. What we see in this case is that as x approaches 1 from below, the function values get closer and closer to 2. So we see that for the function f of x equals x plus 1, as x approaches 1 from both above and below, f of x approaches 2. We therefore say that the limit of f of x as x approaches 1 equals 2. A couple of important things to note about this example. Firstly, we were only interested in what happens to the function values for x values close to 1 and not at 1. We found the limit without actually substituting in x equal to 1. In this particular example, however, the function value at x equal to 1 is f of 1, which equals 2. Since the limit also came to 2, we see that the limit equals the function value at 1, i.e., the limit of f of x as x approaches 1 equals 2, and this is also equal to f of 1. We now want to generalize the preceding result for any function f of x. If f of x approaches L as x approaches a, then the limit of f of x as x approaches a equals L. Let's now look at the function f of x equals x squared minus 1 over x minus 1. We want to get an idea of what the graph looks like. We can factorize the numerator as a difference of squares, and we find that the denominator can cancel into the numerator, provided that the denominator is not 0. In other words, provided that x is not equal to 1. So we find that f of x equals x plus 1, where x is not equal to 1. So this is a straight line graph passing through negative 1 and positive 1 on the x and y axes respectively, but the graph has a hole in it at x equal to 1. In other words, the function value does not exist at x equal to 1. In order to find the limit of f of x as x approaches 1, we can once again approach x equals 1 from both above and below and find the corresponding function values. And once again we find that as x approaches 1, f of x approaches 2, and hence the limit of f of x as x approaches 1 equals 2. You should note that in this particular example, the function value did not exist at x equal to 1, but the limit did exist. So the function value doesn't need to exist for the limit to exist at a point. We now come to the third important example on the limit. Here we have a piecewise function, f of x equals x plus 1 if x is not equal to 1, but equals 3 if x is equal to 1. Once again, this is a straight line graph that passes through minus 1 and plus 1 on the x and y axes respectively, but it's discontinuous at x equal to 1. In other words, we have a hole in the graph at x equal to 1, and the function value at 1 equals 3. So once again we can investigate what happens to the function values as we approach x equals 1 from above and below by substituting values closer and closer to 1 on the x-axis into the equation and then finding the corresponding function values. Once again we find that as x approaches 1 from both above and below, f of x approaches 2. So we can say that the limit of f of x as x approaches 1 equals 2. What's important to note about this particular example is that the function value at 1 is not equal to 2, but it's equal to 3. So we can see that the limit of f of x as x approaches 1 doesn't equal the function value at 1. We'd like to just summarize the important aspects of this example. Firstly, the function value did exist at x equal to 1, and it was equal to 3. However, the limit at x equal to 1 was 2. Thus the limit at x equal to 1 doesn't equal the function value at 1. So we can see from this example that where the function value exists, the limit doesn't always equal the function value. Let's look at the function f of x equals 3. This is a horizontal line that passes through 3 on the y-axis. In this case, we are interested in the limit of f of x as x approaches 0. We can start by plugging in values close to 0 but above 0 on the x-axis and find the corresponding function values. We see that as we get closer and closer to 0 from above, the function values actually stay at 3. We do the same thing but approaching 0 from below, plugging in values closer and closer to 0 but below 0 on the x-axis. And once again we find that the corresponding function values stay at 3. Even though in this example the function values do not approach any particular number but stays at 3 as we approach 0 on the x-axis from above and below, we still say that the limit of f of x as x approaches 0 equals 3. Later on, when we take a closer look at the working definition of the limit, you will see that this is consistent with the working definition. Once again, we have a piecewise function in this example. F of x equals x if x is less than 1, but equals 2x squared if x is greater than or equal to 1. The graph of this function consists of two arms. The left-hand arm is a straight line graph that has a hole at x equal to 1. And the right-hand arm is a parabola, and it does exist at x equal to 1. Let's say we want to find the limit of f of x as x approaches 1. Once again, we can substitute in values closer and closer to 1 but above 1 into the equation and then find the corresponding function values. Note that when we approach x equals 1 from above, we have to substitute our x values into the equation of the parabola. We see that as x approaches 1 from above, the function values approach 2. We now approach 1 from below on the x-axis. We plug in values closer and closer to 1 but below 1. In this case, we are plugging our x values into the straight line graph's equation. We see that as x gets closer and closer to 1 from below 1, f of x gets closer and closer to 1. Note that in this example, the function values approach 2 as x approaches 1 from above, but 1 as x approaches 1 from below. So the function values do not approach the same number. Hence we say that the limit does not exist at x equal to 1. That means that the limit of f of x as x approaches 1 does not exist. So here we have the function f of x equals 1 over x squared. Let's for a moment reflect on what the graph could look like, or would look like. Firstly, 1 over x squared is always positive for both negative and positive values of x. And that means that we'll draw the graph entirely above the x-axis. Then secondly, x can never be 0 because we can't divide by 0, so the graph never passes through the y-axis. Also, as we plug in numerically smaller and smaller values of x, 1 over x squared becomes larger and larger. So that means that the function values are getting larger and larger for numerically smaller and smaller values of x. So the y-axis is a vertical asymptote. Then lastly, as x becomes numerically larger and larger, 1 over x squared becomes smaller and smaller. So the function values become smaller and smaller, and the x-axis becomes a horizontal asymptote. So here's the complete graph. Let's say we want to find the limit of f of x as x approaches 0. Once again, we could use a table and plug in values closer and closer to 0 and find the corresponding function values. But in this case, we'll just use the graph to see what happens to the function values as we get closer to 0. We can start from above 0, getting closer and closer to 0 from above. As we can see, as we get closer to 0 from above, the function values get larger and larger. In other words, they increase without bound. So we can say that as x approaches 0 from above, f of x approaches infinity. We now approach 0 from below. Getting closer and closer to 0 from below, we see that the function values also get larger and larger. So we can say that as x approaches 0 from below, f of x approaches infinity. Note that the function values must approach a unique real number L for the limit to exist at a point x equal to a. If the limit of f of x as x approaches a equals infinity, then the limit does not exist at x equal to a, since infinity is not a real number. So in the previous example, since the limit of 1 over x squared as x approaches 0 equals infinity, we say that the limit does not exist. Let's look at the function g of t equals cos pi by t. We want to find the limit of g of t as t approaches 0. Although we may not know what the graph looks like, we can still find table values to see what happens when we approach 0 from above and below. So approaching 0 from above, we can substitute in values closer and closer to 0, but greater than 0, and find the corresponding function values. In this case, we see that at t equals 1, the function value is negative 1. But for values after or smaller than 1, but above 0, we find the function values stay at 1. We do the same for t values less than 0, plugging in values closer and closer to 0 but below 0. And once again, we have the same pattern that at t equal to negative 1, the function value is negative 1. But for subsequent values closer to 0 but below 0, the function values stay at 1. We now conclude that the limit of g of t as t approaches 0 equals 1. Unfortunately, this is wrong, and we're going to look at why. To try and understand why the limit of cos of pi by t as t approaches 0 is not equal to 1, let's take a couple of values for t smaller than our smallest positive value in the table. One such value is 1 over 2001, which is smaller than 0.001, the smallest positive table value. The function value here turns out to be negative 1, and not 1 as we'd expect it to be. Yet another value for t smaller than the smallest positive table value is 2 over 2001, and here the function value is 0 and not 1. Let's take another value for t, such as 4 over 2001. This is smaller than 0.01, also a table value, and the function value here turns out to be the square root of 2 over 2 and not 1. To see why this is the case or what's happening here, let's solve the equation cos pi by t equals 1. We find that the argument pi by t is 2 pi k, where k is an element of integers. In other words, scalar multiples of pi. So we can see that in selecting our table values for t, we were unfortunate enough to select values that will give us scalar multiples of pi, and hence always a function value of 1. However, when we look at a computer-generated graph of this function, we find that it doesn't stay at 1, but oscillates between plus and minus 1. And hence, the limit doesn't exist. So, this example shows us that it can be dangerous to use tables to evaluate limits with, and henceforth, we will refrain from doing so.